here R, I have to stress the main thing. So this R is a region in a plane. Okay? I still have to have two pieces of information, what the function is and where I'm taking the integral on. Right? I need a function involving two independent variables and also a region in R2. So now you can imagine how many different cases you can have for this region as opposite to an interval in the one-dimensional case. So in a plane, you can have a region as a disk, you can have a region as a rectangle, you can have a region as a triangle, you can have a region as a ellipse, you can have a region as a interior of a parabola, you can have all kinds of different regions. Are you with me? So this is the main complexity. So computing double integral, the most difficult part is how to describe the integrating region. Okay, how to describe the integrated region. So generalizing from a single variable integration to double integration, the main difficulty is to go from integral, which you don't have anything to worry about. They are just two boundary points, to a very generalized region in R2. Okay. So throughout the double integral, we'll also introduce triple integral again. Okay, after the double integral. The triple integral is where you have three independent variables, and the integrated region is going to be a solid region in R3. So it's going to be even more cases happening here. So for double integral, the function is not going to be the difficult part. The region is what we will spend our major focus on. So I will introduce the following 5 different cases for regions. First one is the easiest one, rectangular. Okay, so rectangular region is really the interval in R2. Okay, so interval is the easiest object in R1, and rectangles are the easiest objects, easiest regions in R2. So these are basically just the product of two intervals from AB to CD. So this is the region. So this is our region, so CD. Okay, this is X, this is the 1. So in R1, the integrating region is just a closed interval. In R2, your very similar object in two-dimensional case is going to be a Cartesian product of two intervals. It's just a rectangle. And I'll also introduce Y simple region, X simple region, and then I will introduce polar coordinates, so polar rectangles. And also in the polar rectangle region, so it's R simple regions. So polar rectangle in R, you can see R as the distance, theta as the angle. Okay, so we'll be looking at 1, 2, 3, 4, 5 different regions in double integral. Okay. So even though they seem to be a lot, but this is still a very small family of regions in R2. You can have a lot of different regions, not very regular regions, which is not going to be either one of these 5. Okay, but these 5 different types will cover most of the problems we'll be looking at. So we introduce 5 different types of regions, beginning from the easiest case, rectangular region. Okay, so this is really a pretty easy case we can practice to begin from. And then it will give you a general principle of how to do double integrals. Okay, so now I have 2 pieces of information, f, x, y, as my integrating function, and R as my integrating region is given by x, y, where x is bounded by a and b, y is bounded by c and d. Okay, so which is exactly the picture right over here. Okay, in a double integral of this function, on the region will be written in this notation. And so this is the integral of a function on a region. Okay, so this one is equal to from a to b y dx dy is also equal to from a to b, from c to d, fxy dy dx. Okay, so this will be the formula to compute a double integral if the function has two independent variables and the region is a right angle. Okay, so a couple of remarks I have to make before we practice on several problems. Okay, so basically what I'm saying here is if the region is a right angle, I can take this double integral as a composition of two single integrals. Okay, I can take this as two single integrals. However, when I write it out, I have to be consistent with the variables and its intervals. Okay, so in this case, the interior integration is with respect to x. Okay, so the interior integral is with respect to x because x is bounded between a and b. The interior interval is from a to b. Okay, and then after I take the integral with respect to x, I'm going to do integral with respect to y, and that's why I have the integral with respect to y in the outside. So this is the interval from c to d. So I have to write this double integral in the correct order. Okay, x goes inside, so the interval is with respect to x. Y goes outside, so the interval is with respect to y. So if I change it in a different order, so the interior integral is going to be with respect to y, so that's why I have this interval from c to d. So when I change the order, you can do this if your integrating region is a right angle. And when you change the order of the integration with respect to two independent variables, you have to keep the intervals correspondingly. Okay? You have to keep the intervals correspondingly. Y goes inside, so the interval for y goes to inside as well. Okay? And the most important thing I want to explain is here. Why am I saying this is just a single variable integration? If I'm looking at an interior integration, it is just an integration with respect to x. So I'm going to regard y as a constant, exactly as what we did before. So when I take the integral inside, I can eliminate the variable x. Right? I can eliminate the variable x because once I finish computing the interior integral, I'm going to get a function involving only y. I'm going to eliminate x definitely because you already take the integral with respect to x. So the interior integral will end up with a function involving only y. And then you can take the integral with respect to y with no problem at all. Both of these two steps are single variable calculus. So rectangular case is indeed the easiest case for two reasons. One reason, you can change the order with no problem at all. You can change the order, but you have to keep the intervals corresponding. And also, this is just the two steps of single variable integration. Okay? So I'm going to give you a couple examples. You will be immediately confused. So from 0 to 3, from 0 to 2, okay, 2xy dx dy. Okay, so I want to evaluate this double integral. I want to evaluate this double integral. So throughout the semester, my principle for you guys is, first of all, don't be scared. Everything is still single variable calculus. Okay? Don't be scared. Everything is still single variable calculus. The only thing I'm teaching you is how to reduce a multivariable setting to a single variable case. Okay? So it's just one step away from what you learned before. So don't be scared at all. So in order to do this, I can look at the interior integral with x as the independent variable, y is just a constant. Okay? So forget about the outside integral. Just look at the inside. Okay? So looking at the inside, in order to evaluate an integral, we find the antiderivative. All right? So if I'm asking you, this is the function. I want to find the antiderivative of this function where x is the only independent variable. What is that function? X squared y. Because if we take the derivative with respect to x, where y is a constant, it's going to give you 2xy. Are you with me? So that's the only thing we're doing here. It is just a single variable calculus. And then I need to evaluate from 0 to 2. And to be more clear here, I usually prefer to write it as x equals 0, x equals 2. Then you will know which point, which variable you wanted to plug in for numbers. Okay? So I have done everything in the interior, so outside is still the same. Doesn't change at all. Okay? So this is what we have. And then in the inside, I'm going to plug in x equals 2 and x equals 0. And when x equals 2, what we're getting is 4y. And when x equals 0, this is just 0. So it's going to be from 0 to 3 dy. All right? This exactly justifies what we said before. If I evaluate the interior integral, I'm going to eliminate the variable x. Right? So if you evaluate the interior variable, you're getting a function involving only y. And then you're doing another single variable integration. Right? So finding the antiderivative is going to be 2y squared, and you evaluate from 0 to 3. Or if you want to be more clear to yourself, it's from y equals 0 and y equals 3. So in the end, you're getting 18. Okay, and that's all. Okay, so everything is pretty the same as the single variable integration. The only thing you need to remember is the very first step, when you take the integral in the inside, you're regarding one of the other variable as a constant. Okay, so similar principle as what we did for partial derivatives. I want to verify the following. I can change this double integral into a different order. And this formula says the order does not matter at all. All right? I can take integration with respect to x in the interior or with respect to y in the interior. And the answer should not be altered at all. So I want to verify that. But when I change the order, I have to keep these intervals with the same variable. All right? So it's going to be from 0 to 2, 2xy dy, and from 0 to 3, from 0 to 3 in the interior and 0 to 2 in the outside. Okay? So this is a very simple practice, because if you look at this function 2xy, it doesn't really matter which one you go first. Okay? So the only thing I'm doing here is I change the order from dx dy to dy dx. When I do that, I also switch the intervals as well, right? Okay, so let's do what we have here. So if I want to find the antiderivative of 2xy with y as the variable, what we have? It's going to be xy squared. And then evaluating from y equals 0 to y equals 3. So from 0 to 2 dx. So if you eliminate y in the very beginning, we're going to get y equals 0. It's going to get 9x minus 0. So it's from 0 to 2, 9x dx. All right, so once you take the integration in the interior, you're going to get a function with only the variable in the outside. Okay? And then finding the antiderivative is going to be half of 9x squared, evaluating from x equals 0 to x equals 2. So when x equals 0, this is equal to 0. X equals 2, I'm getting 4 is 18. All right? 18 as well. So indeed, changing the order of integration does not change the final answer. Question?
Is there a quick way to determine which one's easier?
That's a very natural question you can ask. Usually, one method is one direction, or one order is easier than the other. And in some cases, dx dy will be significantly easier than the other, dy dx, or the other way around. So I will give you a couple of these kind of examples as well. Any questions about the principle? What we're doing here, okay? So next, I want to look at slightly more complicated example. So from 1 to 3, from pi half to pi, x cosine y dy dx. Okay, x cosine y dy dx. Still, we just pair off the double integral step by step by taking the variables independently. right? So in the interior, if I'm taking the integral with respect to y, x is constant, right? So from 1 to 3, I need to find the antiderivative of x cosine y with respect to what? What is that?
X
X sine y. And probably you have this experience for dealing with single variable calculus as well. If you're not sure about your antiderivative, you take the derivative with respect to y and see whether you can get back the function. All right? So if you're not sure about the antiderivative, especially involves two variables, I need to take the partial derivative with respect to y and see whether I can end up with x cosine y. Okay? So this is partial derivative with respect to y. You can easily check. This is going to give you x cosine y. So this is the correct function I'm going to plug in here. So y from pi half to y equals pi. Okay? So when y equals pi, I'm getting a sine pi 0. When y is equal to pi half, sine pi half is equal to 1. So this is indeed from 1 to 3 minus x dx. All right? So it's x sine pi minus x sine pi half. So it's going to give you minus x. Okay? And then I'm trying to find the antiderivative of this guy. It's going to be pretty easy. Minus half of x squared, evaluating from x equals 1 to x equals 3. And what we have here is we have to be careful about the numbers. So it's minus half of 9 halves minus 1 half. So it's going to be next 4. Okay? Minus 1. You can change the order for this function as well, from dy dx to dx dy. You can end up with the same number, but only thing different is you're going to take the integration with respect to x, y is the constant, you find the antiderivative with respect to x and everything. So you can change the order as well. So I do want to go back to the question you can ask in terms of you have two different integrating rods.